Welcome to a deep dive. Today we're jumping right into the specs of a really foundational piece of gear, the NTI E-BPT barometric pressure transmitter.
Right. And our whole mission here is to pull apart what can be a pretty dry technical sheet and find the insights that matter for you.
Okay, so let's unpack this thing. At first glance, it's just a small, pretty unassuming piece of hardware.
It is, but it's designed for one really critical task,
Yeah.
just determining atmospheric air pressure.
Which provides that crucial baseline you need for basically any serious monitoring setup.
Exactly. And that singular focus is what makes its operational window so reliable. The source material says it measures from 20.8 to 32 inches of mercury.
Or, for most people, that's 10.2 to 15.7 psi.
Right, pounds per square inch. And what's interesting here is that this range covers, pretty much all standard atmospheric pressures on Earth, from high-altitude facilities down to sea level.
So it's a real workhorse, but for controlled conditions, I'm guessing. The specs say it's only compatible with clean, dry air.
Oh, yeah. This is not something you'd want to survive, like a chemical spill.
Not all.
It definitely needs a clean home. And to give you a picture of it, the unit is made from a durable plastic acrylonitrile butadiene styrene, and it's tiny.
What are we talking? Size-wise?
It measures just about 2 by 3 by almost 2 inches.
Yeah.
So picture something like a small, thick smartphone. It's meant to be mounted and then, pretty much forgotten about.
Okay, this is where it gets really interesting, I think, especially for anyone who's depending on reliable data over the long haul.
Precision is everything in this game.
Let me jump in with the numbers then. Accuracy is listed as plus or minus 0.14 inches of mercury. That's good, but maybe not world-beating for a lab setting.
That's a great point. It's a trade-off.
So are they sacrificing some of that raw precision for, I don't know, ruggedness or something else?
I think you've hit on it. It's a trade-off, but you have to look deeper at the stability numbers. The raw accuracy is one thing, but where this device really shines is consistency. Its repeatability is plus or minus 0.03 in Hg. And the big one, long-term stability, is just plus or minus 0.014 in Hg per year.
Wow, that annual drift rate is microscopic.
It is. I mean, think about what that means for operations. You often use barometric pressure to correct other sensor readings, right?
Mm-hmm.
Well, if your baseline pressure sensor is drifting, all those other calculations get thrown off. The stability means fewer site visits, less recalibration, basically a lower cost of ownership over time.
And that's where that industrial price tag starts to make sense.
Exactly. So how do you get all this precise data reported back without electrical noise messing it up over a long distance?
Well, it uses the industry standard, right?
Yeah.
A 420 mA output needing 8 to 24 volts DC.
Yep. And for anyone listening, that 420 mA signal, it's the standard for a reason. It's just highly immune to electrical interference, which you absolutely need because this sensor is built for scale.
And speaking of scale, let's talk about distance. The source says the standard cable run is capped at 500 feet.
Which is pretty good. But the real game changer is its compatibility with the EFSC fiber converter.
Right, that extender.
If you connect this to the bigger picture, that fiber converter lets you push the sensor up to 1.2 miles. That's 2 kilometers away from the main unit.
That's huge. We're talking about monitoring across massive industrial complexes or like a university campus.
It's what makes it viable for those large-scale projects. You're not just getting data, you're getting data with integrity from very far away.
And since this is a professional piece of kit, it's listed at $555 with a 2-year warranty. It has the compliance markers you'd expect.
Yeah, we see the CE approval and it's TAA compliant. The CE means it meets European safety standards, and TAA means it's good for government contracts. It just frames it as a trustworthy professional asset.
So if we boil this all down, we've looked at a sensor that is hyper-focused on one job. It's built for extreme stability over time, not just initial accuracy.
And with a robust output that's designed for these huge industrial-scale monitoring systems.
So here's a final thought for you to mull over. We've established this thing can report reliable data from over a mile away. The sensor is stable, but that connection is incredibly long. If you're monitoring something critical across that vast distance, how do you ensure the signal stays perfect over that entire path? Does that fiber converter, the EFSC, suddenly become the single most critical and maybe vulnerable component in your whole environmental data picture?